Jnanam paramam dhyayam. Knowledge is supreme.
Let's get started with a few more problems on translational operator for a finite dimension, that is the finite distance, spatial finite distance. And this problem 4 will involve problems on the commutator of the position operator and the translational operator with a finite displacement. So, in the question we have TA is exponential minus I p dot A upon h cross, where p is the momentum operator in 3 dimension. So, we can write this as e raised to minus I px ax. Okay. I can write this hat as the operator px, ax is a position, fixed position, py ay plus pz az upon h cross. So, we are given that p is a momentum operator in 3 dimension and Ri is a position operator in some certain direction. So, Rx or R1 will give me x direction, then I can have y direction and z direction. So, let us start by writing a specific case, like we have to first evaluate Ri Ti A, okay, and then we generalize the result. We will generalize the result later. So, as we know that the momentum operator Px, Py and Pz commute with each other, so will be Tx, Ty and Tz. So, this T cap A, I can write it as T cap x Ax, sorry there will not be a cap, Ty Ay and Tz Az. So, these translational operators will also commute with each other. So, when we are taking the commutation relation, we have to use this hint. So, these operators x, y, z are in 3 directions, 3 translational directions, that is the 3 axes x, y and z, and these Tx, Ty and Tz commute with each other, right. Now, since we have this, let us evaluate Ri T A I. Okay. So, Ri T A I, you remember we have done such exercise in tutorial 5. In that we have evaluated this quantity and this came out to be, just try to recollect, AI times T A I. This is what we had obtained in tutorial 5. And remember, we will use these relations while evaluating the general result. So, Ri, commutator of Ri and Pi will be 0. Okay. This we should recollect, and we know that Ri Pi is nothing but IH cross. We have seen these commutator relations. These are the general relations which we have seen. In general, we have seen the expression of Ri and J, Ri and Pj, okay, that is delta Ij. When I and j are equal, they will not commute, and when R and I and j are unequal, they would commute in this particular case. So, this is what we have here. So, will be Ri T J A J. This would imply this, remember, because Pi depends on Ti depends on Pi. So, if I have a Pj, then I have a Tj which will be equal to 0. Okay. So, using 1, 2, these two things, using equation 1 and 2, what we obtain is, let us write now Ri, this is position operator, T A. Okay. So, Ri T A, T A can be written as T x, T y, T z, okay, and Ri will commute only with T I. So, I will have Ri T I A I times, that is T x if I take, and here if I take, let me keep it I only. Okay. So, I will have a T j A j T k A k. These, remember, these are operators and we need to denote it by cap. So, this is a R I T I A j, which is nothing but A I. Okay. I will have a AI and this quantity, that is T I A I, T j A j and T k A k, which will give me back this term. Okay. In the question, we have this, in the question we have that we have to determine how the expectation value of R will change under this transitional. So, let us now consider a system in state psi. So, let psi be the state of the system, and now we have to remember this. It is important to note here that translational operator is unitary. Okay. This is one thing you must remember. And now, when we suppose we apply a translation operator, that is T A, what do we obtain? So, consider this T dagger A, this is the operator T A, R I. So, we are finding out the expectation value of R I, this is what we are asked to find, but on this state we are applying the translational operator. So, T on psi on the right and T dagger on psi on the left, because T will become T dagger. Psi T dagger A I R I T A I. So, this we will evaluate. Here what I said is, I will use R I T A I commutator plus T A I R I. I will substitute for this here. We have seen what is the commutator of this. Commutator of this was A I T A I, correct. So, commutator will give me this, and the second term is this term. Okay. So, what do I get next from here? This will be nothing but T cap A I. I have got R I, which I can actually take outside. In the next step I will do that. T cap A I. This is the first term, and the second term is T dagger A I, and I have a T A I R I times psi. Okay. Now, these two terms I will simplify. A I is a number, A I can be taken out, it is a number, not an operator, sorry. So, A I can take outside very well, and I have a T dagger T, which will give me just 1. Okay. this is what I have, correct. And when Ri is operated on A, and this term will give me 1. So, let me write here. Okay. So, this is the expectation value of Ri on the state psi, and when you operate the translational operator, it is getting shifted by amount Ai. So, in the end what we see is that there is a shift in the position by Ai. So, the position is shifted by Ai, thus the expectation value of Ri is shifted by Ai when one operates a translational operator. Okay. So, there is a shift by amount R Ai. Okay. So, this is the fourth problem we did. Let us go to the fifth problem. Fifth problem is divided in 3 parts, and it is slightly lengthy, but it is interesting to check these relations, commutation relations, and what will be the displacement operator and all things. And this was discussed in the last part of the lecture, and you were asked to prove some of the relations. So, we have put some problems as the tutorial problems, so that you actually sit and solve them. So, first part, in the first part you are given a coherent state which is defined as the eigenstate of the ladder operator, and you are given a relation. So, for any operator or any complex number alpha, you are given alpha is e raised to minus alpha square upon 2 e raised to alpha a dagger. So, small a dagger, okay, and 0. Just recollect that and this operator or the normalized eigenket of A has eigenvalue A alpha. So, when A is operated, A dagger or A operator A is operated on alpha, you get eigenvalue A alpha. Okay. This you have to remember. Now, the next step would be that we have to define we have to calculate x square p square in this coherent state basis. So, for that you need to do some algebra, few hints I will give, and you can maybe use those hints to work further. So, let us define dimensionless position and momentum operators as A plus A dagger by 2 and P as A minus A dagger by 2 times I. So, this is a position operator x and the momentum operator p, which are defined in terms of the operator A, which has eigenvalue alpha when you operate it on the eigenket alpha. Okay. So, now let us rewrite x and p in terms of A and A dagger. Okay. A and A dagger. So, what will be in terms of A and A dagger? A will be equal to x plus I p cap upon 2, and A dagger is simply the complex conjugate, you can see here, correct. So, we know that for simple harmonic oscillator, we have this relation capital X is nothing but m omega upon 2 h cross inside the square root x cap, and P is nothing but 1 upon 2 h cross omega m inside the square root p cap. So, capital X and small x are related by this relation. Okay. We have defined capital X in terms of dimensionless variable. So, we have to now, and remember P and X and P are our regular or usual position and momentum operators, right. So, it is now easy to evaluate what is x. This is x is what we are going to evaluate. X we had defined as a plus a dagger by 2. So, first we will evaluate x, then we will evaluate x square, then p and then p square. So, expectation value of x on ket alpha will be 1 by 2. I have a dagger A. So, I will write A alpha plus alpha A dagger alpha, correct. And when you operate this, this will give me an eigenvalue alpha, this will give me an eigenvalue alpha square, alpha star. So, I will have alpha plus alpha star, and these are normalized eigenket. So, these are of the form R, I can write it as real part of alpha. Okay. Now, in the same manner you evaluate x square will be, you will find when you solve this, you will have the real part of alpha which we evaluated will be square plus 1/4. So, please check this, check yourself. Okay. Then I will write what is my P. We have seen that operator P was I A minus A dagger, okay, and I have skipped this, but you must remember that when there is a hat, it is an operator notation. So, I have I by 2, and then I will have alpha minus alpha star kind of a term which is equivalent to, or which can be written as imaginary part of alpha. Okay. Similarly, you evaluate this and you will find that imaginary part of alpha square plus 1/4 is what you obtain. Now, the next step would be to calculate delta x dot delta capital P. Okay. Delta x dot delta P will be square root of, you know the definition, x square minus expectation value of x square into similarly P minus P square. We have evaluated all these, and when you substitute this, you will have something like this. Now, you will substitute for capital X and capital P in terms of small x and small p. This is what we have, right. So, when I substitute for these, I get delta x dot delta p as, in the operator notation, let me be very explicit. So, this relation is nothing but Heisenberg uncertainty principle delta x dot delta p should be less than or equal to h cross by 2, okay, right. So, this coherent state, note, coherent state alpha actually achieves the minima in Heisenberg uncertainty principle relation, which is equal to the value of the uncertainty principle because of capital X and capital P. We have seen that. The second part or the B part you are asked to calculate the exponential E B if commutator of A and B is equal to a constant, then you have to show that e raised to alpha A dagger e raised to minus alpha star A dagger is having some relation like e raised to alpha square by 2 e raised to alpha A dagger minus alpha star A. So, we have this relation and we are going to use Becker-Hofstadter formula. So, what we have, let me write here as B A e raised to A comma B, okay. And you have this equal to e raised to A plus B times e raised to AB commutator of AB by 2. So, using these relation and applying Becker-Hofstadter formula, we have e raised to alpha A dagger and another term is e raised to alpha star A. Okay. This expression I can rewrite using this result, I can rewrite this as e raised to, I can write this as alpha A dagger, okay, this term in minus alpha star A. So, I have used this times e raised to alpha A dagger minus alpha star A divided by 2, and this will be A dagger alpha A dagger minus alpha star A, and I can have alpha square outside and commutator of A dagger and A dagger is 1. So, I have alpha square by 2. So, this is what we have proved. It is just one step. Okay. These relations will be useful in proving other results also. So, now the C part is that we can rewrite the coherent state in terms of the displacement operator. Can we do that? Now, let us write the displacement operator, we have to write in terms of the coherent state. So, the coherent state given to us is e raised to minus alpha square by 2 e raised to alpha A dagger. This is what is given to us. And remember, we know that when you operate annihilation operator on any in a state 0, you will obtain 0. Okay. It will not go further. This is the end of the ladder. So, I can write this again as alpha square by 2 times e raised to alpha A dagger. I can write this as e star A. I can just multiply by some coefficient, it will not matter. we have used this. Okay. Now, remember we had this relation over here. Okay. I will use this relation in this expression. So, when I use this relation, I will have this term times this, and I have one exponential minus alpha square by 2 in the expression already. So, I will just end up having e raised to a dagger minus a star a on alpha, and this is the definition of displacement operator, and hence we can prove that this is the coherent state can be written in terms of displacement operator. And you have to show in this part that the displacement operator is unitary. This is explicitly seen, it is very simple, e raised to alpha a dagger minus alpha star a, and d dagger alpha will be e raised to alpha star a minus alpha a dagger. Okay. So, when I take d alpha, d dagger alpha, d alpha, so u dagger u is 1, that is it is unitary operator. It is very simple, you can see it without even solving. Okay. So, these exercises, and you had in your lecture few more exercises, try and solve it and see if you can do solve those exercises which were discussed.